geez, this presenter looks like he knows what he's talking about. Sorry, I can't continue. Okay, all right. So today we're going to be exploring memory in Ruby, and I'm going to talk about building a compacting garbage collector. But first I want to say thank you to all of you. Thank you so much for having me. It's a pleasure to be here. I'm really honored. Colombia is amazing. This city is so beautiful here. I can't believe how beautiful it is. I heard that there was extremely good coffee here in Colombia, so I explored and tried some of the local coffee houses. I'm just kidding. I did actually get some good local coffee, so don't worry. And I also drank out of a bathtub, which was kind of weird. My name is Aaron Patterson. I'm known on the internet as Tenderlove. You can ask me about that at the after party tonight. This is my icon. If you don't recognize me here, this is what I look like online. I used to have a lot longer hair and not as much gray hair either. I'm on the Ruby core team and the Rails core team, so if you want to talk to me about Ruby stuff or Rails stuff, either one of those, I love talking about Ruby and Rails, so please come talk to me later and we can chat about anything. I work for a very small startup company. They're based in San Francisco. I live in Seattle though. It's called GitHub. We host code online. If you haven't seen the website, I recommend you go check it out. I really like using Git. I really enjoy using Git, but I'm not going to force push it on you. I live in Seattle, Washington, and I work remotely. I work remotely from Seattle, Washington, and you can tell that because if you get on my machine and you run git remote, you'll see that it says Seattle. So I'm trying to think of more Git puns. Okay, come on, give me a break here. I've got two cats. They enjoy writing code with me. This is one of them. His name is Gorbachev Puff Puff Thunderhorse. He's the more famous one, I think. Here's another photo of him with an owl. He looks like an owl. This is my other cat, Choo Choo. She really enjoys boxes. Like, she'll sit in a box, and she's always sticking her tongue out. Just her tongue is always out all the time. Anyway, I have stickers of my cats, so if you like cats or like stickers, then you can come talk to me and I will give you a sticker of my cat. So yes, come say hello and I will give you one. I'm also on the Ruby marketing team. The Ruby marketing team is something that I just made up today. And I am the only person on the marketing team so far. But I think in the Ruby community, we're really known for being friendly and kind and stuff. And I think that we might be too friendly and too kind. So for a minute, I'd like to throw a little bit of shade and tell you something that's on my chest. I need to get it off my chest. And that thing is I don't like JavaScript. I'm sorry, but I just think it's a really bad language. I really don't understand why people use it. I mean, I know that you need to use it in the browser, and that's fine, but your server-side code can be anything, so why would you punish yourself with JavaScript there? And many people say to me, oh, I don't like context switching. It's so hard for me to think in JavaScript in the browser and then switch languages to the server side. They always make this complaint to me, and I just think to myself, well, handling a DOM exception is completely different than dealing with a bad file descriptor. So as soon as you are switching to your server-side code, you have to switch context anyway. So what is the problem? Just use a good language on the server. It doesn't need to be Ruby, but it shouldn't be JavaScript. Anyway, my final argument here is I want to show you a bit of code. Here's some code that I wrote. And this is Ruby code, and this is some JavaScript code that I wrote as well. And I'm gonna display them side by side here, so you can see the two of them together. So we got Ruby on the left side and JavaScript on the right side. And if we run the Ruby code, I'll cat the file and then I'll run it, and you'll see, oh, it prints out just what we expected, right? That's pretty cool. Now let's try to run the JavaScript code and see what happens. So I'll cat the JS file and try to run it, and then you see we just get an exception, and then my terminal explodes. So this is why you should be using Ruby. It's way better. So I'm going to talk about a Mark compact garbage collector. This is something that I've been working on at work for a while, and this has interested me for a long time because I'm interested in reducing fragmentation in memory and trying to reduce our overall memory footprint in production code. And one of the things that I wanted to focus on is copy on write optimizations from a compacting garbage collector. So we're going to talk about those topics here today. And I wanted to call this overall umbrella this under the term of exploring memory in Ruby. So first we're going to talk about copy on write, what copy on write is. Then we're going to talk about building a compacting garbage collector in MRI. And then I'm going to talk a little bit about memory inspection tools. Now, this is a warning. This is a low-level talk. We're going to be talking about some low-level stuff, but I want to make this talk accessible to everybody in the audience. So for new people who are out there, I have some goals for you to think about during the presentation. Just think about these overall topics, like what is copy on write, what is compaction, and I want you to just pay attention to the definitions of things, not necessarily exactly how they work, because I want you to think someday in the future, well, hey, I've heard about these terms, or I want this thing to happen, I've heard about this somewhere, and I can go look it up somewhere else, right? So you don't need to necessarily understand the entire presentation, just know that it's something that you can do. For experienced people like who already know about these high-level terms, pay attention to the algorithms that I'm going to talk about and the implementation details as well. My goal is that everybody in the audience is able to come away from this and say, so that's how that works, whether it's copy and write optimizations or GC algorithms or whatever. So first we're going to look at copy and write optimizations. And this is shortened to COW frequently, C-O-W, and I always think of this COW. But I'm going to refer to it as COW or COW from now on because it's much shorter than copy on write. So what is copy on write optimizations? Simply what it is we don't copy something until it gets written to. So we have something and we copy that. We only copy that thing when it is being written to, and I'll give you a concrete example. So for example, in Ruby, Ruby strings are copy on write. So if we create a string here that's 9,000 characters, we can get the size of that string, and we see the size is a little over 9,000. And if we duplicate the string, and we check the size of that duplicate string, you'll see that it's only 40 bytes. It's actually much smaller than the original size. Now, on that next line, I actually mutate the string. I change that copy. And as soon as I change the copy, or as soon as I change the duplicate object, that string gets copied, and we see down here that the string has been copied on write. We wrote to the string, and because we wrote to the string, now the object gets copied. And the same thing happens with arrays. So I'm not going to walk through every single step of this, but we have the exact same behavior with arrays in Ruby. When we duplicate them, they don't actually get duplicated. Now, for some reason, this isn't the case with hashes. When we duplicate a hash, it actually does get copied, and maybe we can fix this, I'm not totally sure. But the overall idea of this optimization is that when you copy some object, if you copy something, as long as you haven't changed that thing, then there's no observable difference between the original one and the copy. So there's no reason for you to actually do the copy. Now, this optimization isn't just limited to Ruby programs. We can use this optimization in various different places on our machines, and one famous place where we use this is the operating system. The operating system takes advantage of this optimization, and it performs this optimization every time we create multiple processes using the fork system call. So when you fork a process, the operating system actually makes a copy of that process, and that copy is your child. So here's an example where we have a forking example where we allocate a very large string. We fork the process, so we have a child process. We have our initial string here of 9,000. As soon as we do this fork, we don't get a copy. There's no copy, no actual copy of the string going on. But as soon as we write to that string in the child process, then that chunk of memory will be copied. So the operating system automatically deals with that copy for us. So the Ruby programming language has nothing to do with it. It's just the operating system. Now, the way that this actually works is we have, for example, operating system memory pages. So we have a parent process here, and along in that parent process, that's our memory for the parent process, and it's a giant string that contains a bunch of X's. Now, when we fork our child process, the child process actually just creates pages that point back up to those parent process pages. So it's not actually copying it, it's just pointing to it, saying like, here is the memory. Now, as soon as something gets written in the child process, the operating system automatically copies down to the child process. So we wrote in the middle of the string, we wrote that Y to the middle of the string, so that page gets copied into the child process. Now, an interesting thing about this is that when we looked at the Ruby example, the entire string was copied, right? But with the operating system, only a certain chunk of it is copied, and that's one page width. And that page width is defined by your operating system, and it's about 4K. So this is what we call a copy on write page fault. So we have a page fault, and we copy that page to the parent or child process. So why is copy on write important to us? At GitHub, we use Unicorn, which is a forking web server. And we actually do forking in many other places throughout our code base, but this is a really famous example. People who use this web server are doing forking, using a forking web server. And the way this forking web server works is we have a parent process, we create a parent process, it creates a bunch of child processes, and those child processes actually serve the requests. Now, if we load Rails inside of each of those child processes like this, then we're going to have 3 different copies of Rails in memory at a time. What would be nicer is if we actually had the parent process load Rails, then we fork a bunch of child processes, and now those child processes will point at that copy of Rails, so we only have 1 copy of Rails in our system's memory. So we have those children pointing there. Now, the point of doing this is it reduces our boot time. Obviously, we only load Rails once rather than 3 times. It decreases memory usage because we're only keeping 1 copy of Rails in memory at a time. And I want to say that this is actually how it works today. This is, if you're using Unicorn, this is the way that it actually works. Now, this isn't the type of optimization that I'm interested in necessarily, but it is one way that we take advantage of copy on write. So what I'm interested in doing is reducing page faults, these faults that happen at runtime in the child process. Now, what causes these page faults? The thing that causes page faults is mutating shared memory. Anytime we mutate that memory that the children processes are pointing to, we get a copy. So what does that? What mutates shared memory? Very frequently, it's the garbage collector. So what things does the garbage collector do that impacts that actually does these writes and can be bad for copy on write? Well, it used to be during the mark phase of our GC, the GC would go through every single object and mark those objects, and that would cause your program to be your entire heap to be copied to the child process. It would store the mark bit on every single object. So for example, we'd walk through these. Let's say we have a parent process with a bunch of Ruby objects and a couple of free spaces and a child process that's pointing at those. Now, when the garbage collector goes through its mark phase in the child process, it'll say, okay, I'm going to set the mark bit here on this object, and then unfortunately that means it gets copied. So we copy that object, and it keeps progressing through, marking each of these objects, and each of those objects gets copied to the child process. And this is because we had the mark bits stored on the objects themselves. Now, the problem here is that that graph was not totally truthful. The operating system copies an entire page. So actually what happens is when we mark one object, an entire page worth of objects gets copied. So for example, we may actually, on that first object getting marked, we may actually copy the entire page rather than just one at a time. So it's even worse than what I had showed you before. Now, there's an optimization called Bitmap Marking, which was introduced to Ruby a while ago. This is a technique, and essentially what this does is it says, okay, when we set that mark bit, we take the mark bit off of the object and we store it into a table on the side. So rather than marking the object itself, it sets a mark bit in a table. And that table is a very small table. This table will get copied between processes, but it's actually a very small amount of memory, so it doesn't matter as much. So we set those bits in a table rather than on each object. Now, the next problem that our garbage collector gives us is object generation. And you may or may not know this, but Ruby's garbage collector is a generational garbage collector. And each time a GC occurs, an object can increase in age. It gets older. So every time there's a GC and an object survives the GC, that GC gets older. Now, unfortunately, today, we store the age of the object on the object itself. So when the object gets older, we store that age on the object. And that means that we end up with the same problem that we had with bitmap marking, where each object gets copied. Now, we have an optimization for fixing this. There's a way to fix this. Well, not necessarily fix it, but to work around it. And the way we work around it today is with a gem called Nakayoshi fork. So if you're using Unicorn in production, I recommend that you check out this gem. And the way that this gem works is essentially on the principle that generations are bounded. So an object can only get so old. When an object gets to a certain age, it doesn't age anymore. It's just considered old, and we don't change the object's age. So once it gets to that age, we just stop. Now, what the gem does is, well, the other theory is that objects created before forking will get old. So say we load up all of Rails into memory, we're pretty certain that all of that code that we loaded is going to be old after we fork. We're going to keep that code in memory for a very long time, so it probably will get old. So if we believe these two principles, then we can deal with this problem by just GCing a few times before we actually fork a new process. So if you look at the source code for Nakayoshi fork, it's actually a very simple program, and essentially here's the core of it. All it does is just GC in a loop a few times. And then it calls super and does your fork. That's really all it's doing. So it GCs a bunch, all of your objects are now old, and now they won't be written to in the child process. Now, there's one more problem where the garbage collector causes writes to your memory, and this may be surprising and unfortunate, is object allocation. So this is a third place where the garbage collector impacts copy on write. This one's kind of surprising, but just allocating an object will impact the performance of this optimization. So for example, let's say we have a parent process that looks like this and a forked child process that points there. Now, the child process allocates a new object, and it's going to allocate it inside a free space. So say it allocates it there. Now, unfortunately, we wrote to a bit of memory, and as you recall, the operating system copies an entire page when we write to memory. So instead of just copying that one little square, it's going to copy this entire thing, and we end up with just writing one object means that we have copied a whole bunch of objects to the child process. So we duplicate that memory. So the question is, how can we reduce the space, or how can we get rid of those free spaces inside of our memory? And the answer to this is GC compaction. So the way that this will work is, say we have some memory that looks like this, 2 pages. Now, in a worst case scenario, we would copy both of those pages because an object would get written to the free space. Now, if we compact all of this before we fork, so say we move all of those around like that, now the worst case scenario is in the child process, our child process points at one page, and that page is totally full, and then the other page points at one that's empty, and it ends up that only this one page gets copied. whereas before we could have had 2 pages get copied. So the idea is that we have GC plus, I presented 3 different ways to make the garbage collector copy on write friendly. Bitmap Marking, which we talked about, that's already in Ruby. You're using it today, so you don't have to worry about it. A problem with generational age on each object, and the way we deal with that is with this gem Nakayoshi fork. We've dealt with those 2 problems. But the third problem, heap compaction, that's something that we have not done yet today. So the next topic I want to discuss is implementing heap compaction, how we can actually implement this thing in our garbage collector. So let's take a look at GC compaction. This is a project that I've been working on at GitHub, and I want to talk about how it actually works internally. So we're going to talk about the algorithms as well as the actual implementation details. So what is compaction? I mean, we saw an example earlier. Essentially, all that we're doing is taking these spaces that are in memory and trying to fill them. So we move all the objects around such that all the free spaces, or all the objects are grouped together and all the free spaces grouped together like this. And hopefully the program continues to work after we do that. That is the goal. The goal is we'll move this stuff around and your program still works. So why do we want to do this compaction? For me, there are 2 reasons. One is I wanted to reduce memory usage. And the other reason is that I've been talking to a lot of people about this problem, and there's been some sort of, I don't know, I guess meme throughout Ruby history that this is an impossible thing to do. Many people kept telling me that this is impossible. Unfortunately, those people were implementing other Rubies, like JRuby or Rubinius. They told me this is impossible, and I believed them. And one year I gave a presentation about garbage collection, a technique I thought would help, and Koichi, who is a VM author, came up to me afterward and said, you know, you said that this compaction is impossible. Why do you think it's impossible? He asked me. And I didn't have a good answer. I didn't know why it was impossible. So I thought to myself, well, if I don't know why it's impossible, I have to try it out. Let's find out, I'll find out for myself why it's impossible. So I had to try. This is the second reason I wanted to do this. So let's look at some compaction algorithms. There are many different compaction algorithms. I'm only going to talk about one of them, and that's the one that I'm using for the implementation here. And this is called a 2-finger compaction. So I chose a compaction algorithm called 2-finger compaction. Now, this compaction algorithm has some disadvantages. I'm going to talk about the advantages, but we'll talk about the disadvantages first. First off, it is slow, unfortunately. The second problem is that objects move to random places throughout your memory. If you look at other compaction algorithms, they move them all together, which can actually speed up your program. This one moves your objects into random locations, which can unfortunately slow down your program. Now, it may or may not slow down your program. There's no telling. But unfortunately, these are pretty bad. These 2 attributes are pretty bad compared to other compaction algorithms. So let's look at the advantages of this algorithm. This algorithm, as far as I know, only has one advantage. And that advantage is it is easy. So that's why I chose this algorithm. It's actually very easy to understand and relatively easy to implement. So why not do this? We'll do the easy one first. If we can actually prove that it works with the easy one, then we'll move on to the harder ones later. So we can divide this algorithm into 2 steps. The first step is moving objects, and the second step is updating references. So first, let's go over object moving. This is a visualization of objects in Ruby memory. So imagine this is what your memory looks like if we were going to put it onto a slide. Each object is a fixed width. It's only a certain amount. It only uses a certain amount of memory. And each location in memory can either be empty or full. It can either have an object or it can be free. Now, 2-finger compaction works by placing 2 pointers or 2 fingers on either side of the heap. So we have 2 pointers there. The pointer on the left is called the free pointer, and the right pointer is called the scan pointer. Now, the free pointer moves to the right until it finds an empty slot. And the scan pointer moves to the left until it finds a full slot. And then it exchanges the two. Now these two don't have to move. It's already on a free slot and a full slot. So we just swap them. And we repeat this process over and over. So we also set it what is called a forwarding pointer. So the object that was in B is now in 1, so we leave a forwarding address of 1. So we repeat this process. This moves forward to free, and this one moves backwards to object. Then it swaps them, and it leaves a forwarding address. And we keep repeating this process until the two fingers meet. So one more, and then they meet. So once they've met, we've got all of the objects grouped together. Now our next step is to update references. Now before the objects were moved, let's say they looked something like this. So our Ruby code maybe is a hash, and it contains a symbol and a string. And maybe the hash is at 4, and the symbol and string are at 6 and 7, for example. Now, after we move the objects around, it's going to look something like this, where our hash is still pointing at those locations, but the string and symbol have moved. So we have to update the references for each of the objects. And the way that we do that is we just create a new pointer, and all it does is scan forward until it finds objects with references. It looks at the references, finds the forwarding addresses, and just changes the references to point at those new forwarding addresses. So then it points at 5 and 3, and we continue until we're done changing all the references. When we've reached the end, it's done. Finally, we change all the forwarding addresses back to free slots, and then we're done with the algorithm. It's just that easy. So let's take a look at a few implementation details. I'm going to dive into some of the actual code that I'm using here to actually implement this. So you can get this code if you want to try out GC compaction. I have a fork here on our GitHub fork of Ruby. This works against Ruby 2.5, trunk Ruby. So if you want to try it out, you can. It introduces a new method called gc.compact. So it's a manual process. You have to actually compact the heap yourself. The way that we've tried this out, we've actually deployed this to production. And the way that we used it in production, we're not using it in production anymore because we don't want to run an edge version of Ruby all the time. But we tried it out to make sure that it actually works. And the way that we're using it is we say in the parent unicorn process, we say, okay, load all of Rails and its dependencies. This isn't the actual code. We load all of Rails and the dependencies, and we load the application, and then we compact the heap, and then we fork all of our child worker processes. So that's the way that we're using it in production. So we load all that code, we compact everything together, and then we create all of our child processes. So I want to go over some of the changes that we made or that I made to gc.c in order to implement this. Nearly all of the changes were in gc.c in Ruby source code. This is where the garbage collector lives. So I'll talk about each function and what part of the algorithm it belongs to. So there's a new function introduced called gcMove, and all that does is it just swaps two things and leaves a forwarding address. So it just does this step of the algorithm. That's it, just the swap. I also introduced a new type of object that's hidden from the user called a tMoved object. So this forwarding address here is called a tMoved pointer. So it just points where to go now, where it should be. There's also a new function introduced called gcCompactHeap, and what it's responsible for is moving those fingers closer together. So it walks through each of those, moving those pointers, and calls gcMove to do the actual swap. Then there's a new function called gcUpdateObjectReferences, and all that does, just like the name implies, is change those references like that. Just change the forwarding pointer. Now, unfortunately, every single object in Ruby stores pointers to objects in a different way. So the way that a hash points to keys and values is different than a way that an object points to instance variables, for example. So if you look at this gcUpdate, this function, you'll find essentially a giant switch statement, and all it does is call out to other functions like gcref update array that updates arrays. We have one for updating objects, one for hashes, one for methods. Everything that Ruby contains, these different functions will update those references. Now, the other thing that I've introduced, and this is a bit of a hack, is something called pinned bits. This is a new bit table, and what this bit table does is it prevents some objects from moving. Sometimes we don't want objects to move, and we're going to talk about that. This is a limitation of the current compactor that we're going to talk about. So, what objects can move? Let's make a list of. We're going to make a list of what types of objects can move. So right now, today, so far in this presentation, everything can move. We can move everything. That's great. That's really great. We can move all objects everywhere. Now, we have a little bit of a problem where we have to find references. When we need to update references, we need to be able to find those references. So I'm going to talk about finding references and how we use those pinned bits. So, for example, let's say we have this pure Ruby reference. It's just a class. It points at an instance variable. No problem. The foo object points at the bar object. It's easy for the garbage collector to come in and say, okay, well, I know that foo points at bar because these are pure Ruby. They're implemented in Ruby, so I know how foo references bar. I know the internal implementation details. They're both pure Ruby. Since they're both pure Ruby, it's easy for the garbage collector to update those references. Now, what happens if foo is implemented in C? The GC doesn't know how C data structures work. It doesn't know anything about your C data structures. So you write some C code. It doesn't know the layout of your structs or anything. So let's say foo is implemented in C and bar is implemented in Ruby. Now, unfortunately, the GC doesn't understand how these are connected. It doesn't know what makes this arrow. And because it doesn't know what makes that arrow, it can't update that reference. Now, one thing that we can do is, there's a trick that we can do. Let's say you have this. You wrote some C code, and your C code references a Ruby object. Now, when the garbage collector runs, let's say it collects bar. It says bar needs to go away. It's time to collect it. If it collects it, now foo is pointing at a bad reference, and your program will crash. Everything will blow up. So if you write a C extension, how do you prevent this? What code do you write to prevent this situation? This is a problem that you have today with your C code. You have to do something to prevent that from occurring. And what you have to do is, in your C code, you have to call a function called rbgcmark. You have to mark that object in order to let the garbage collector know, hey, I have a reference to this. I don't want it to go anywhere. Okay? Now, another problem is, let's say the compactor moves bar. Let's say it moves it. Now foo is pointing at a tMoved object. And unfortunately, that tMove object, it's meaningless. It's not what you wanted. It's not what you're pointing at. So your program will crash again. So the way that I fix this in the garbage collector is we say, okay, well, if you mark rbgcmark, or if you mark an object with rbgcmark, it means that there's a reference that I can't update. I don't know where it is. So this rbgcmark will pin bar and prevent it from moving. So bar cannot move. We mark it in this pinned bit hash table. So I changed this function to rbgcmark. What it does, it does two things. It marks the object, and then it pins the object in the pinned bits table. So before my patch, all it would do is mark the object, but today, in my branch, it will mark the object and pin it. So our new steps for GC compaction are we do a full GC so that all objects get pinned. Any of your C extensions will still work. Then we compact all the objects, then we update references. So, okay, now what can move? Everything can move, except objects marked with rbgcmark. Okay, so that's okay so far. We've given up a few objects. But we have some other movement problems. I thought that this algorithm would be easy until I actually tried implementing it. So I want to talk about some of these problems that prevent objects from moving. And this is hash tables. We'll talk about hash tables first. We mostly know how hash tables work. You have an object and you calculate a hash key, and that hash key puts the object into some bucket in the hash table. Now, unfortunately, in Ruby, the default hash key is the address of the object in memory. That means that where that object is in the hash table depends on its location in memory. So if I move the object, all of a sudden its hash changes. And it means you can't look that object up in the hash table anymore. So we don't want to move those. So in order to fix this, today what I'm doing is the compactor will pin these. It won't move them. But we can fix this. We can just cache the hash key. If you ever use an object as a hash key, we can cache the hash value on the object. So I haven't implemented this yet, but it's a limitation today. So what can move? Everything can move except objects marked with RBGC mark and hash keys. So, all right. Good job, Aaron. Let's look at another situation. How about dual references? Let's say we have this situation where we have a C object that points at a Ruby object and a Ruby object that points at another Ruby object. But the author thought to themselves, bar won't move because it's automatically marked. So I don't need to use RBGC mark. Now, unfortunately, the compactor may move this. We don't want it to move, but the compactor may move it. So if it does move that, we end up with a situation where the reference for Baz gets updated, but the reference for foo does not get updated, and the program can crash. So we end up with these situations where we have dual references between C and Ruby objects. And this is code that I found in the wild. This isn't a thing we do in Ruby core necessarily. This is just somebody's C extension. In order to fix this, what we have to do is we have to call RBGC mark or use only Ruby. And if you go, this is something I found in the message pack gem. We use message pack at GitHub, and we were getting crashes in production, and it was exactly from a situation like this. So if you go look at this pull request reference down here, you can see how to fix these types of errors. So unfortunately, this is a situation we just have to fix. So what can move? Well, everything, except objects with marked with RBGC mark and hash keys and dual reference objects. Now let's talk about global variables. Now, this is a very common, I'm going to show you a very common practice in C extensions, and that's it. We define a class and we assign that class to a global variable in C. Now, unfortunately, we have the same situation here. The GC can't update a global C variable. It doesn't know about this reference. It can't fix it. So what do we do in this situation? In this situation, we're using heuristics to pin the objects. We know that it's common for people, if somebody calls RB-defined class, we know that you're calling that in C, and that you're probably going to keep a global reference to it. So we'll pin those. Okay. Only C programs ever call that function, so we know that those ones should stay pinned. So what can move? Everything, except objects marked with RBGC mark, and hash keys, and dual reference objects, and objects created with RB-defined class. Now let's look at another one. Let's look at string literals. Oh, man. This is kind of depressing to work on. Actually, it was really fun to work on, but looking back on all the stuff that can't move. So, okay, let's look at string literals. We have an example program here, just a very simple program. Foo prints out a string, hello world. Now, when Ruby compiles this program, it turns the program into instruction sequences. If you look internally, there's an object called an iseq object. It's a regular Ruby object, but it's implemented in C. Now, this iseq object, it points at a Ruby array of literals. So every time it encounters a literal, this hello world, it turns it into a Ruby string, and it puts it into this Ruby array. Now, at the same time, while it's compiling your program, it turns your program into bytecode, and that bytecode is written in C, and we learned about some of this stuff yesterday. So this bytecode is written in C, and these bytecodes are just literally binary data. And this binary data contains a pointer back to this Ruby object, this hello world object. The bytecode contains an address of that object. So if a literal moves, if I want to move that hello world, I can't. Because if I move it, I have to update the bytecode. Now, unfortunately, updating bytecode is hard. It's possible, it's just very, very hard, and I haven't implemented it yet. So this means that literals can't move in this branch. So today, all right, let's go over this again one more time. I think one more time. What can move? everything, except objects marked with RBGC mark, and hash keys, and dual reference objects, and objects defined with RB defined class, and string literals. It seems like nothing can move. But there is good news. There's good news. Most of these can be fixed. So all of these situations that we've talked about and looked through, there are situations that we can fix. It just requires work. So for example, the bytecode thing, we can fix that. I just have to write the code to do it. And for most of those cases, that's all we have to do is do a bit more work. All of them except for the RBGC mark situation, those ones we cannot fix. So today, just even with all of these exceptions, even with all these rules that I've shown you, 46% of the objects in your heap can move. Here's an example Rails application. I took an image of the heap. So this is what it looks like before we compact. Each of these vertical bars represents a page. Red objects, or red bars, represent the number of objects that cannot move. Green bars represent the number of objects that can move. And this is before we do a compaction. This is what it looks like after we do a compaction. So you can see we've moved all of them to the side. Okay, so we've implemented GC compaction. We know what that looks like. I want to talk about one more topic, which is inspecting memory. So for this part of the talk, I want to cover a few memory inspection tools. And the reason I want to do that is it's important for you to measure your impact. Anytime you're doing any kind of work, you need to measure the impact. If you've created a new feature, you need to see how many people use it. You need to measure how slow your pages are so that you can improve the speed, but you always need to measure. And since in this case I'm working with Ruby's memory, I need to be able to measure our impact. So let's look at a few ways to inspect your program's memory. The first one I want to look at is the easiest one, I think. It's called objectspace.dumpall. This is available in your Ruby today, I think as of Ruby 2.1 or something. So you can use this today. And all this does is it dumps all of your objects to a JSON file. Everything in memory, it just dumps it out to a JSON file. So here's an example of usage. We're just opening up a JSON file and dumping everything out. So we can measure the number of objects it takes to boot Rails, for example, by doing this. Really easy. This is an example of how I was measuring this with the compactor. We say, okay, I'm going to boot up Rails with production, and I'm just going to compact the heap and then dump out all the objects to a JSON file. And when you look at the JSON file looks something like this. There are lines in the JSON file. Each line represents an object, and that line is just a hash. This is an example of one object out of there. I've prettied it up a little bit here. So this is this is the same data, but just formatted a bit more nicely. You'll see here, some of the things that are important to me are the address. Like right there, we have the address of the object. This is where it actually is in memory. Also, we know references, so we can see what this object references, and that's a list of other addresses. So if you look up, you can take that address and look in the heap to find, or in the dump to find that object. Also, you can look at size, so if you care about figuring out where your large objects are, you can check out the size of those things. So you can figure out how much memory the object is consuming. So as I said, address equals location, and this is important to me. The location of the objects is important to me because I'm rearranging all of the objects in memory. So if you know a little bit about Ruby's garbage collector, you can make a graph of what the memory looks like. So we'll take that heap dump, that JSON file, and turn it into a graph so we can visualize what the memory looks like. So this is what it looks like if we were to take all those objects and graph them together. All the red dots there represent objects, all the white dots are empty, and you can see that this heap is fragmented. And what that means is that there are a bunch of white dots everywhere in there. We have a bunch of space. And that space is what we're trying to get rid of. This is a graph for a Rails 4.2 application. So this is what it looks like before we do compaction. Now, after we do compaction, it looks like this. So you can see that there is a large change. We've moved all the objects to the side. However, there are some over there on the right that still remain, which is what we are discussing. So I've made another graph of this. This is exactly the same graph, except that the red represents objects that cannot move, and the green represents objects that can move. And if we run compaction, this is before compaction, and if we run compaction, you can see that all the green moves to the side. So these graphs, I just hacked together some scripts to generate them, and you can go grab them here. There's one RB file in there. You can use it with your Ruby today if you want to inspect what your heap actually looks like. So go grab that there, and if you want to know more about how we actually generate that graph, come talk to me later. So let's talk a little bit about inspecting copy on write memory as well. So we looked at Ruby's heap, but my goal here was to fix copy on write or improve copy on write usage. So the way that we measure that on Linux is using the proc file system. And all you really need to do is you look at this file called the smaps file. I don't know why it's called that. I'm sure there is a good reason, and I just not have thought of it. But if you get the PID of the process and you look at this smaps file, and it'll contain a bunch of entries in it, and this is one entry. At the top of the entry, you can see the address range of that page, and using that address range and the object ID, the address of the objects, we can figure out where the objects live in reference to the kernel's allocator. So we have that range there, and our object range, our object addresses from the heap, and now we know which section of the smaps file to look at. The other important thing to look at in here is the RSS and the PSS. So RSS, you're probably familiar with that. When you do a top or whatever, you look at the RSS of your process to see how much memory it's consuming. I am here to tell you that value is misleading, unfortunately. The other thing to look at is this value here, the shared dirty, and those are the number of pages that are shared between processes. This example is from a process that hasn't been forked yet. So in order to calculate RSS, we do that by summing shared clean, shared dirty, private clean, and private dirty from that file. So that's how we calculate RSS. Now PSS is the shared dirty divided by the number of processes that point at that shared page, plus shared clean, plus private clean, plus private dirty. So if you look at this math, you can tell the more processes that share it, the lower the PSS will be. So that's the number that you want to look at. So for example, we have a unicorn parent process that takes, it's reporting its RSS to be 3 megabytes, and the child process will also report the same thing. So you might think to yourself, oh, our unicorn processes are using 7 megabytes of memory. But they're not. You actually need to look at the PSS and sum those. Your unicorn processes are taking 3.6 megabytes of memory, not the actual 7. So here's an example of copying memory. I want to show you a graph of these PSS and RSS. So all this is a simple program that creates a string, and then in the child process, it writes to that string. So it writes to the string 9,000 times, and then tells me, hey, Aaron, go take a sample. So if we take that and we graph it over time, each time it pauses, we can create a graph that looks like this. So this is what those values look like as we decrease the amount of shared memory. So you'll notice here the RSS stays the same the entire time, but the shared dirty pages decrease and the PSS increases, right? So our goal is to make sure that shared dirty stays as high as possible and that PSS stays as low as possible. And RSS has no meaning to us. So in this particular example, what I did is I said, okay, in order to measure the amount of impact that our compaction has, I said, okay, I'm going to create a new process. I'll start the GC. I'll fork a new process. Well, I'll compact the heap and then fork a process and then fill out the entire memory so that we can measure how much the impact is. Now I'm going to show you some numbers that I am not happy about. So here's an example of the PSS with no compaction, and it's about 2.6 megabytes. And if we look at the PSS with compaction, we can see that it's about 2.5. So with compaction, our total savings are only about 150K. So this is sad to me. Now, the good news about this, as I said, we can fix all those objects that can't move. This is actually just on an empty program. It's not actually on a real Rails application. We're still collecting this data in production, so I can't tell you what a real app will look like. So hopefully I can tell you that soon. But I want to wrap this up by saying, well, our compaction savings are unknown at this point, but we can improve it. So we should be able to see a larger improvement as we get those objects to move. Use object space when you're trying to debug any type of Ruby level memory issues. If you actually need to look at the, operating system or process level, use this file, this maps file. And again, I want to cover why, I want to end by coming back to this topic. Why compact? Why do this? Now, to me, the biggest reason is that somebody actually told me that this was impossible, and I believed it. I assumed that that was true. And I wish that I hadn't done that. I wish that I had questioned that assumption and actually just given it a try. If I had done that, I could have been giving this presentation 2 years ago rather than today. So if I can end this with anything, it's question your assumptions. Think about those things that you just take for granted and believe to be true every day. Question that and see if it actually is true. Take the time to figure that out. Thank you very much.